Alright, so in this video we're going to be looking at implicit differentiation. So implicit differentiation is a very important skill that we're going to be using to differentiate some graphs that are not functions, right? So what is it specifically? We use it for implicit equations, as the name would suggest. So what is an implicit equation versus an explicit equation? Hopefully this is something you've seen before in maybe your pre-calc classes, but just as a quick recap, an explicit equation is something like all of the equations that we've been thus far differentiating. So something like y is equal to x plus 5. This is explicit, where we have one variable written in terms of another variable. This is an explicit equation. Whereas if we were looking at an implicit equation, this is one where, again, this is not a function. This is not a function where we have more than one variable in play, right? Like, for example, x squared plus y squared is equal to 25. This again, this would be the equation for a circle, which we know to not be a function as it does not pass the vertical line test. But yeah, so an implicit equation is one where we have more than one variable here. We have x and y. Whereas an explicit is one where we're writing, y in terms of x. So how do we go about implicit differentiation, differentiating these implicit equations? Well, without getting into too much detail of the reasons why we're doing it, because again, I just want to show you how to do these problems. Basically, all you do is you approach it very much like you would any other differentiation problem, except slight there's a slight extra step or slight nuance here. For example, if we were trying to find the derivative of our function y squared minus 5x cubed is equal to 3y. Essentially what we're doing here is we would differentiate every time we see y, any term with a y in it, we differentiate it just as we would any x, except afterwards we just add the term dy dx to the end. Again, in this video I'm not going to go over what exactly the reasoning is there, but just remember if there's a y that we're differentiating after we write the derivative, we immediately follow up with dy dx. Then we would isolate for that dy dx and solve for it, which would give our answer. And I'll just show that again more clearly as we work out this problem. So firstly, we take the derivative, right? And like I said, each time in the derivative when a y is involved, you include dy dx. And this dy dx is what we're ultimately trying to solve for in the problem. So in this case, right, what is the derivative of y squared? That's just 2y. Remember to add dy dx. Next, minus 5x cubed. The derivative of that, we bring the 3 down. That gives us minus 15x squared. And this, again, we don't add anything else there. And this is equal to 3, derivative of 3y is 3, dy dx. And again, this is Leibniz notation. Just know, for example, if we were differentiating something like x, this term is also present. For example, when we did this, right, we have minus, or we get minus 15x squared. But here we would write dx, which is just 1, right? It's just 1. So there's no point, there's no need to write it. But that is also present. In this case, because the variable is different, we actually see it as something explicitly different here. So anyway, so now that we have this, we want to isolate everything. We want to basically gather all the terms that have this dy dx component onto one side, let's say the left side, and everything else goes onto the right. So we keep this 2y seems to be glitching. Just give me a second. All right, hopefully it's going to stop glitching now. But anyway, so we take our 2y dy dx, keep it on the side. We bring over the other term that has a dy dx over here, giving us minus 3 dy dx. And we move this term that doesn't have a dy dx onto the other side, and that gives us 15x squared. So now that we have our terms kind of gathered in this way, we can essentially factor out this dy dx term here. So this we can rewrite as dy dx times 2y minus 3, right? If we multiply that out, we would end up with the same thing. So we factor out the dy dx. This is equal to 15x squared. Hopefully you see where we're going with this. Now we divide both sides by 2y minus 3. And if we do that, again, I'm running out of space. So, or let's do it over here. So if we do that, we end up with dy dx is equal to 15x squared divided by 2y minus 3. And so this then is going to be our derivative. Again, our dy dx. If you remember again, this Leibniz notation dy dx, this is something we've seen before. It's not something that's new necessarily. So here this this looks so messy. But yeah, this dy dx is just referring to the derivative of this implicit equation. So whenever we do this, we're just isolating and trying to solve for the dy dx. So hopefully this is making some sense. Let's look at a couple more problems just to get more practice. So let's say we're given a function y to the fourth minus 3x is equal to x cubed plus 2y. So here, again, we can see that this equation involves two variables, y and x, so we know that this is an implicit equation and we use implicit differentiation. So let's just differentiate everything here, but every time we have a y component, we just make sure to add or tag a dy dx to the end of that. So the derivative of y to the fourth, that's 4y cubed dy dx minus 3, which is equal to 3x squared plus 2 dy dx. Next, we gather our terms that have dy dx onto the left and the other terms onto the right. So we get 4y cubed dy dx minus 2 dy dx is equal to 3x squared plus 3. We factor out the dy dx term here, dy dx times 4y cubed. Let's rewrite that. 4y cubed minus 2 is equal to 3x squared plus 3. Divide by 4y cubed on both sides in order to solve for our dy dx, right? dy dx is equal to 3x squared plus 3 divided by 4y cubed minus 2. And this is the answer here. So again, it isn't something that's crazy difficult, really. We're just doing normal derivatives as usual, but whenever we have a y term, we just tag this along, and we're isolating and solving for that. All right, let's look at another problem. Again, feel free to pause the video, by the way. I didn't mention this. Feel free to pause the video, obviously, and give these problems a try yourself, and then you can look at the solution or how we do this. So let's say we're given something like this. Sine of xy. What is that? And also the sine of xy we're saying is equal to 10x. So this is another implicit equation. We have two variables that we're dealing with here. So how do we approach this? All right. So we start off again. This is chain rule, clearly. We start with the sine, then we differentiate what's inside. So we get derivative of sine is cosine. Cosine xy times the derivative inside here. This is going to be product rule inside. So inside we end up with 1 times y plus x times y prime, or x times, again, the derivative of y is just 1, but we can, so x dy dx, really, if you want to write it like that. But also know that if you want to save space, instead of writing dy dx, you can replace that with y prime. And so these are equivalent, so whatever you want to do. So we have this x dy dx, and this is equal to 10. It's equal to 10. Okay, so now we end up with y plus x dy dx is equal to 10 divided by cosine of xy. We then get x dy dx is equal to, again, this is all just basic algebra. So again, I'm not going to be explaining everything as we go along. Now we're left to isolate for dy dx. Isolating for dy dx just gives us our answer, 10 divided by cosine xy. Again, I mean, here, let's actually do this. What we can do here, actually, is we can simplify this a bit just to make it a bit easier for ourselves. This 10 divided by cosine xy. This is basically 1 over cosine of xy times 10. What is 1 over cosine? 1 over cosine is secant, right? So we can just rewrite this as 10 secant xy minus y, right? Now, isolating for dy dx, we get our answer of 10 secant xy minus y divided by x. This here is our answer. All right, so hopefully this is making sense. Let's look at then how we can actually use implicit differentiation in different circumstances, right? There's different problems that you may see. They might not just be given an expression, but something more in specific context. So we know that the equation for a circle, right? An equation for the graph of a circle is an implicit equation, right? It's not. It's an equation that describes something that isn't a function. So, for example, if we're given an equation for a circle x squared plus y squared is equal to 4, and we're then told here, so if we're given a function, again, this is a function, or no, again, I can't say that, but this is a equation for the graph of a circle. So this is the graph of some circle, again, that has radius 2, but anyway, what we want to do is we want to find the equations for the tangent lines when x is equal to 1. So when x is equal to 1, what is the equation for this tangent, these two possible tangent lines that we can get here, right? That's what we're trying to find. So how do we go about doing this? Well, we can use implicit differentiation. Why do we need to use implicit differentiation? Well, because if we have y is equal to mx plus b, this is the form of the equation for a line. If we have this, then, or again, if we want to write it, it might be more convenient actually to not use this form, but rather to use the y minus y1 is equal to m times x minus x1. But in any case, if we need to figure out this m, this slope, we have to use the derivative. With this, so we're using the derivative. We're going to use implicit differentiation to find the derivative of this in order to figure out our m at x equals 1. So, how do we do this? We can first figure out what our y1 and our x1 are by simply plugging in these values into the equation. We have the equation for this function, for this graph, right? So if we plug this in, we see that we are given our we're given our x value already. So it's just 1 comma some y value. Plug that in, 1 squared plus y squared is equal to 4, y squared is equal to 3, y is equal to plus or minus square root of 3. It makes sense that it's plus or minus because remember we had one tangent line over here and the other one over here. So this one's the positive. This is the 1 comma square root 3. This is 1 comma minus square root 3. So yeah, this is our point. So we're almost halfway there with this equation, right? We have 1 comma the root 3, and the other equation would have 1 comma minus root 3 for the points of y1 and x1. So now that we have these points, now let's go about differentiating this so that we can then plug in the values here to figure out the m. So to differentiate x squared plus y squared equals 4, that's very easy. It's just 2x plus 2y dy dx is equal to 0, because the derivative of 4 is 0. Next, we isolate for dy dx. So dy dx is equal to minus 2x divided by 2y, right? Minus 2x divided by 2y. The 2's cancel, so we just get minus x over y. This is what we then plug in our x and y values that we have. Plugging in 1 and root 3 gives us a slope of -1 root 3, -1 over root 3. For the other one, so we call this m1, and the slope for the second equation, or second tangent line, would just be positive root 3. So now we have everything we need to come up with the equations for these tangent lines. We have the points, and we have the slopes. The slope here is -1 over root 3. This one is positive 1 over root 3. So if we want to write out our equations, we end up with 1 minus root 3 is equal to -1 over root 3 times x minus 1. This is the first tangent line. The other one is going to be y plus root 3 is equal to 1 over root 3, again positive here, times x minus 1. So these are the equations for the two tangent lines of our circle x squared plus y squared equal to 4 at the point x equals 1. So you can see hopefully how we're able to use implicit differentiation and why it is very useful for different types of problems. All right, let's see one more problem. Or you know what, actually, I think this video is already getting pretty long. So let's call it here, and in the next video, we'll actually just look at how we can use implicit differentiation to find things like horizontal and vertical tangent lines. So look out for that video. But that brings us to the end of this one, where we looked at implicit differentiation. Hopefully, if you found this video useful, please show your support by liking and subscribing, leave in the comments any questions that you may have, or recommendations for videos that you'd like me to make in the future, and I'll see you in the next one.